So with all that in mind, this previous example was just to sort of motivate the idea of a hypothesis test. Hypothesis tests are typically broken up into steps, and I'm going to break down each of those steps for you, but really you can see that it's very similar to how we would have worked out calculating probabilities of observing sample statistics, just like we did in the previous example. So in this case, let me just remind you of the data, right? We were interested in the population parameter mu, right? That was the true mean weight of the chip bags manufactured by this particular company, okay? So that's the characteristic that we're interested in. I've written down the population parameter mu, and I've written it out in words what that mu in this case means. Next, we want to define the null and the alternative hypothesis. So remember, null hypothesis, I usually write as HO, and the alternative hypothesis, I usually write as HA. The null hypothesis, HO, is usually the thing that we assume to be true. There's usually an equal sign involved. In this case, where there's this hypothesis that mu is 50, right? So that's making the assumption here. The null hypothesis is that the company is filling the bags appropriately to 50 grams on average. Is filling bags to 50 grams on average, okay? Our alternative, the thing that we might be gathering evidence for that we think might be true, it's usually going to have a less than sign or a greater than sign or a not equal to sign. That information will be given in the question. In this case, we were sort of thinking about the fact that maybe this mu was less than 50. We were really concerned that they were underfilling the bags. So I'll just write that in math language, mu less than 50, and then also in words. So the company is underfilling the bags. So some number less than 50 grams on average. Okay, for hypothesis tests, we have a test statistic, okay? And that's essentially going to be very similar to a z-score, okay? So I put sort of a general formula here for you. The test statistic is usually your estimate of your parameter, so that's your statistic, minus your hypothesized value under the null hypothesis divided by your estimates of standard error. And so in this case, for this particular problem, I would write out x bar minus mu naught, so that's the value of the mean under the null hypothesis. Maybe I should write that in words. Value of mean under h naught. So that's this number here. This is my mu naught here, okay? And then, so that's my estimate minus my hypothesized value. And then my standard error in this case is sigma over the square root of n. So if I were to plug in the values for this particular problem, I'd have 49.75, subtract off 50, divided by 50, divided by the square root of 40, because I'm sampling a size of 40 in this particular case. So let me plug that into a calculator and see what I get. All right, and I'm just realizing here as I plug this into my calculator, I plugged in 50 there for the hypothesized, for the standard deviation, and instead that should have been 0.5. That was given in the problem and I've just messed that up. So when I plug this into my calculator here, I'm getting 3.16, okay? And that's a value here that's gonna fall on the standard normal distribution, the Z distribution, okay? And that comes from the fact that this piece here, this x minus sigma over the square root of n, right? That follows very similarly to, let me go back here, to this piece here, right? Where we said, oh, okay, if we have something that looks like this, it's gonna follow the standard normal distribution. So once we've got that, next we're going to go through and work out the p-value. So that's the probability of observing the test statistic that we did, or something more extreme than what we did, if H naught is really true. So in this case, I'm just going to draw you a picture so we can sort of talk about what's going on. Oops, that doesn't look quite right. There we go. So I'm going to plot on this z-score of minus 3.16. And my p-value is going to be all the values to the left, right? So those are values. This one sort of corresponds to the x-bar being 49.75. That looks really messy. Let me fix that. 49.75, right? And all of these here are values that are associated with the mean being something less than that, okay? And so we work out that area or that probability to the left. That's because we're interested in the mean being less than 50. And the way that we're going to do that is using that p-norm function in R. So in this case, I'm going to put in 3.16. You can just leave it like that if you want, because it's a z-score. You can also tell it that for z in particular, the mean is 0 and the standard deviation is 1. Okay. And that should spit out an answer. That's going to tell you the area to the left. Oops, and this should be minus 3.16, shouldn't it? There we go. Or if you wanted, you don't even have to put in those arguments, as long as the mean is 0 and the standard deviation is 1. So we could just do p-norm of minus 3.16. And if I plug that into R, I'm going to do that right now, right into that console. When I do that, I got 0.00078. Okay, which is very, I think that's almost exactly what we got before. Okay, so again, that's the probability of observing a test statistic as or more extreme than what we did if the null hypothesis, and that was in this case that mu is equal to 50, is really true. Now here's where things get interesting, is we sort of say, well, okay, well, what's the cutoff value where we're going to say that probability is so small that we're going to say, you know, not cool, our original assumption must be wrong. And that's going to be specified by our error rate. I'll sometimes call that alpha. So in this case, we're going to use alpha is equal to 0.05. This alpha is very similar to or related to the confidence. So if alpha is equal to 0.05, that means that our confidence is 1 minus that. So in this case, it would be 95% confidence. Very similar to, we talked about that when we did confidence intervals. So that's sort of our level where that's our cutoff. Anything where the probability is less than 5%, we're going to say, wow, that's a really small probability. And in this case, if the p-value is less than the alpha, we're going to reject the null hypothesis. We're going to say maybe our original assumption wasn't true, and we're going to reject it. If the p-value is low, the null's got to go. If the p-value is larger than that, if we get something larger than 5%, we're going to say, well, you know, that might have happened. And we're going to say, well, that doesn't really give us any evidence to say that the null hypothesis isn't true. So we're just going to stick with the null hypothesis in the meantime. So in this case, our p-value was 0.0007. And my alpha was 0.05. If we compare those two, the p-value is definitely smaller. So we're definitely falling, in this case, into the rejecting the null hypothesis category. So I'm going to say reject the null hypothesis. Okay, so we're going to reject the idea that the null is 50, and we're going to conclude here that there's significant evidence for the alternative hypothesis. There's significant evidence to say that the mean is greater than 50, or less than 50, right? It was underfilling them. So I'll just say here, with 95% confidence, we conclude that the true mean weight of these chip bags is less than 50 grams. And so quite often in these sentences, you'll include the p-value so the reader can make their own sort of judgment. So there's my p-value, okay? So I'm rejecting H naught. We have evidence to say HA is true. And in this case, HA was that mu was less than 50.